Japan spent over $85 billion building a train that hits 375 miles per hour. That's faster than most commercial planes. But in this video, you will find out what nobody's telling you about this engineering marvel that took 60 years to create. October 1st, 1964. 6 in the morning. Tokyo Station. A sleek white and blue train pulled out of the station, beginning what would become one of the most celebrated journeys in transportation history. This was the Tokaido Shinkansen, the world's first bullet train, and Japan was about to show the world something nobody had seen before. Just 9 days before the Tokyo Olympics opened, Japan unveiled a train that could travel 130 miles per hour. Most trains in the 1960s were crawling along at 60 or 70 miles per hour. The Japanese had literally doubled the speed of rail travel overnight. Before the Shinkansen, getting from Tokyo to Osaka took 6 hours and 40 minutes. That's a full workday sitting on a train. The economy was bottlenecked by geography. The Shinkansen cut it down to 3 hours and 10 minutes. Same-day business trips between Japan's 2 biggest cities became normal. And here's what blew everyone's mind. The trains ran on time. The average delay was 36 seconds, including earthquakes and typhoons. Japan had built the first dedicated high-speed railway line in history. Standard gauge rails, elevated tracks through cities, tunnels through mountains. The Zero Series trains were inspired by the DC-8 airliner. That bullet-nosed profile is pure aerodynamics. But while the Shinkansen was changing Japan in the 1960s, Japanese engineers were already dreaming bigger. In 1962, Japanese National Railways began research on magnetic levitation. They asked a simple question: what if the train never touched the track? The concept was wild. Use superconducting magnets cooled to -269 degrees Celsius to levitate a train 10 centimeters above the track. Then use magnetic fields to propel it forward. No wheels, no contact, no friction. In 1972, they ran the first successful superconducting maglev test. The train actually floated. By the 1970s, Japan had built a 7-kilometer test track in Miyazaki Prefecture. The results kept getting better. In 1997, they opened the Yamanashi Maglev test line. Over 200,000 people took free test rides. The trains routinely hit speeds over 310 miles per hour. In 2003, a maglev train set a world record of 361 miles per hour. April 21, 2015, 10:48 a.m. The L0 series maglev reached 375 miles per hour. 49 JR Central employees were on board, covering 1.1 miles at a velocity most commercial jets don't achieve at cruising altitude. To put that in perspective, the fastest train currently operating anywhere is China's Shanghai Maglev at 268 miles per hour. The Japanese maglev record is nearly twice as fast. So here's what Japan decided to do with this technology: build the Chuo Shinkansen, a maglev line connecting Tokyo, Nagoya, and eventually Osaka. The journey from Tokyo to Nagoya would take 40 minutes. The same trip on the current Shinkansen takes between 90 minutes and 2.5 hours. Tokyo to Osaka in 67 minutes total. The engineering required is absolutely insane. We're talking about 286 kilometers of track between Tokyo and Nagoya, about 90% underground. The L0 series trains use superconducting magnets cooled with liquid helium to -269 degrees Celsius. These aren't your regular magnets. We're talking about neobium titanium alloys that become superconductors when they're cooled to just a few degrees above absolute zero. The train starts rolling on rubber tires, then begins levitating at around 100 miles per hour. Once it's floating 10 centimeters above the track, Magnetic forces propel it forward. When the superconducting magnets on the train pass over these coils, they induce currents that generate both lift and propulsion. The system is self-stabilizing, meaning if the train drifts too close to one side, the magnetic forces automatically push it back to the center. The nose design went through over 5,000 hours of wind tunnel testing. Engineers discovered that at these speeds, even small imperfections in aerodynamics create massive drag and noise. Each train can carry up to 728 passengers across 16 cars. The interior is pressurized to prevent ear discomfort from rapid altitude changes in mountainous terrain. When you're moving 728 people at once, the per-person energy cost becomes surprisingly reasonable. But let's talk about the cost. When Japan first estimated the cost in 2007, they came up with 5.1 trillion yen. By 2011, that grew to 9 trillion yen, about $82 billion. In October 2025, JR Central announced the total had ballooned to 11 trillion yen. That's roughly $85 billion for just the Tokyo to Nagoya section. The costs kept climbing because of rising material prices: steel, copper, concrete. Labor costs increased dramatically after 2021. Unexpected challenges in mountainous terrain. Standard tunnel boring machines had to be specially modified to handle these conditions. The scale of excavation is mind-blowing. Workers are removing enough earth and rock to fill 23,000 Olympic-sized swimming pools. That's 56.8 million cubic meters of material that needs to go somewhere. Environmental regulations require careful handling and storage. JR Central is using the excavated material to fill valleys and create new industrial land, but local communities are worried. In heavy rain, these filled areas could become unstable. The 2018 Hokkaido earthquake showed how artificial fill can liquefy during seismic events. Japan sits on the Pacific Ring of Fire, making earthquake resilience critical. The tunneling work happens 24 hours a day in 3 8-hour shifts. The temperature inside these tunnels often exceeds 100 degrees Fahrenheit from the heat of machinery and the earth itself. The Maglev costs at least 5.5 times more than the original bullet train, even after accounting for inflation. Central Japan Railway Company is shouldering most of the costs themselves. In 2016, the Japanese government provided a 3 trillion yen loan, about $20 billion. The original plan called for opening in 2027. That's not happening. A more realistic target now is 2034 or 2035. One of the biggest obstacles has been Shizuoka Prefecture. The governor refused approval because of environmental concerns about the Oi River. JR Central's surveys found the tunnels would cause 2 metric tons less water per second to flow into the river. For people who depend on that river, it's serious. Once the water's gone, it never comes back. Without Shizuoka's approval, construction stalled on a 9-kilometer section critical to the entire project. The human cost has been significant. In October 2021, a 44-year-old tunnel worker was crushed to death by falling rocks in Gifu Prefecture. At least 4 other major workplace injuries have occurred in Nagano Prefecture alone. Despite these challenges, JR Central is pushing forward. They're confident they can open the line by 2035. For comparison, the Tokaido Shinkansen currently carries over 160 million passengers per year. Think about what 40-minute travel between Tokyo and Nagoya means. People could live in Nagoya and work in Tokyo. Real estate developers are already planning for this shift. Property values in Nagoya have been rising in anticipation. When the line extends to Osaka, 3 major metropolitan areas with over 50 million people will be connected by travel times under 70 minutes. Tokyo's population is aging. and the city needs younger workers. Nagoya has a lower cost of living, but fewer job opportunities in certain sectors. The fundamental challenge: you can't use existing tracks. A maglev requires completely new guideways, completely new stations, and completely new everything. You're building an entirely parallel transportation system from scratch. China is developing its own high-speed maglev with similar capabilities. Europe remains skeptical. But Japan isn't building this just for transportation. They're building it as a statement. Since the original Shinkansen opened in 1964, more than 10 billion passengers have ridden various Shinkansen lines. And in all those billions of trips across 6 decades, not a single passenger has been killed or injured due to a derailment or collision. Not one. That safety record is unmatched. The maglev has been designed with this legacy in mind. The system includes automatic braking that engages if the train exceeds safe speed limits. Seismometers along the entire route detect earthquakes and can stop trains within seconds. Japan experiences thousands of earthquakes yearly, so this isn't theoretical. During the 2011 Tohoku earthquake, the Shinkansen's early warning system stopped 27 trains before the main shock waves hit. The maglev inherits these safety systems and adds new ones. Because the train levitates, there's less risk of derailment in the traditional sense. But the guideway integrity must be constantly monitored. The trains have multiple emergency exit points and fire suppression systems. JR Central has conducted over 200 emergency evacuation drills. When this train finally opens between 2034 and 2037, it'll be the fastest train service in the world by a significant margin. Passengers will board at Shinagawa Station in Tokyo, float 10 centimeters above the track, accelerate to 314 miles per hour, and arrive in Nagoya 40 minutes later. No vibration, no clickety-clack sound. Just smooth, quiet forward motion at a speed most people have only experienced in an airplane. This is more than just a really fast train. It's Japan's answer to the question, what comes after the bullet train? The answer, apparently, is a train that doesn't even touch the ground. If this deep dive into Japan's maglev project got you thinking about the future of transportation, hit that like button and subscribe. Drop a comment below about whether you think other countries should invest in maglev technology or stick with conventional high-speed rail. And if you want to see more videos breaking down massive engineering projects, hit that notification bell so you don't miss out.